The mapping rule method is not a tedious one, and we can quickly implement it, especially with the use of a calculator in order to find points on the graph. However, there are times when we need to come up with a graph fairly quickly because we may need the graph as an instrument to solve another problem, something maybe even deeper. In cases like these, it is best to find strategic x values. What exactly do I mean by that? Well, the goal is to think of specific values of x that will reduce the exponent of the base of the function to small numbers. For example, -1, 0, or 1. Small exponents will simplify our computations significantly, and it may reduce the process to purely mental computations, things that we can do very quickly mentally. Let me show you exactly what I have in mind. So here is the same function. I'm going to keep using the same function. And here is the exponent, -2, x plus 5. Let's focus on x plus 5. Well, imagine that I let x equals -6. I just pick -6. If I plug in -6, -6 plus 5 will reduce to -1 easily. And then -2 times -1 will be +2. So nice. We all know how to square 3, right? 3 squared is equal to 9 easily, and you can quickly continue like this. So -6, in my opinion, becomes a strategic x value that we should definitely work with if we want to sketch super quickly. So then we're going to have x equals -6. That means that f of -6 will be equal to 1/2 times 3 to the -2, and then substituting -6 in place of x will give us this, and then -3. Now I will just simplify. Now I'm going to show you more steps than needed because I want to make sure that everybody can follow me, but there's certainly a few steps that you can just easily do mentally. So continuing, we're going to have 1/2 times 3 to the -2 times -1, because -6 plus 5 is -1, minus 3, which will be 1/2 times 3 squared minus 3. And this will now give us 9/2, because 9 times 1/2 is the same thing as 9/2 minus 3. And then look at this. I can continue with a common denominator, or I can just quickly remember that 9/2 is 4.5. And 4.5 minus 3 will give me 1.5, which is 3/2. And so easily, just like this, I get a point on my new graph. What I want you to notice here is that unlike the mapping rule method, we don't need to begin with a point on the parent function. We don't have to do that. We just practically pick an x value, plug it into the function, simplify, and get the y values. Now, some of you may be thinking, can I just pick any x value? And the answer is yes, any x value. But remember, we want to be strategic. We want the calculations to be fairly simple. So this is why you want to think a little bit more carefully before you just start dumping x values into the function. So -6 is one of those strategic x values. Here you can see the same calculations that we just derived for x equals -6. And now I would like you to think about the other strategic values of x that we can work with. For example, we can consider x equals -5, because if x is equal to -5, the exponent will simplify to 0. Notice that by substituting -5 into x, we will have -5 plus 5, which is equal to 0. And this means that the entire power will simplify to 1, because 3 to the 0 is equal to 1, leaving us only with 1/2 in the first term. This is why -5 is super convenient. What could be a third strategic value of x? It could be -4. If we substitute -4 into x, then -4 plus 5 simplifies to 1. And the entire exponent simplifies to -2, and this allows us to carry on fairly simple computations to get a y value of -53/18, which rounds to 2.94, -2.94 approximately. Here you can see all calculations at once for the 3 initial values of x that we chose. Remember that these values of x were chosen because they reduced the exponent x plus 5 to -1, 0, or 1. This simplified our computations significantly. After finding the previous points, it is also useful to try to find the intercepts. The y-intercept is an easy point to find. I will show you how to do that, but the x-intercept will not be so trivial. Sometimes it is impossible to find the x-intercept without logarithms or a graphical tool. I will show you such an example a bit later. I will start by letting x equal 0, and then I will find f of 0. This is the y value when x is equal to 0. Here you can see that I substituted 0 in x. I am now simplifying the exponent. You can see that it reduced to -10. In the next step, I will turn the negative exponent positive, and I will have 1/3 to the 10. And 3 to the 10 is a pretty large number, and most likely a calculator will be needed in the process. This is why I don't always consider the y-intercept a strategic point. While it is easy to let x equal 0, computing the y value may not always result in easy mental computations, but nonetheless, very often is a useful point to have on our graphs, and we should feel comfortable computing its coordinates when desired. Let's take a look at the rest of the computations. You can see the large values in the numerator and denominator of this final answer. This is in a sense what we expected when we saw that we had 3 to the 10. When you are ready to plot this point on the xy plane, it is good practice to re-express it in decimal form. The y value is approximately -2.9. Therefore, you can interpret this point as 0, -2.9. You can see it right here, right? Here I have it as a fraction, but this fraction is approximately -2.9. Always remember that the x and y intercepts are points on the graph of a function. For this reason, it is important to state them as order pairs. This is an order pair. Very often we get a bit lazy and we say that the y-intercept is -2.9. And many teachers will allow it. But in a sense, this is mathematically inaccurate because an intercept is a point on the graph of a function. So it cannot equal to just a number. It is an order pair. I want to encourage you to always put an effort in expressing your work in a proper mathematical manner. Paying attention to the little details can make a big difference and help you stand out from the crowd. So always 0, and the y value. Now we will try to go ahead and find the x-intercept. As always, we will begin by letting f of x equal 0. This is the same as saying y equals 0. So in order to proceed with the x-intercept, we're going to let y be equal to 0, or f of x equals 0. So we are going to have 1/2 times 3 to the -2, x plus 5 minus 3 equals to 0. And now, like with any equation that we're trying to solve, our goal is to isolate x. So in order to do that, I'm going to have to add 3 to both sides to bring it over to the other side. And then I'm going to have to get rid of that 1/2. So then we're going to have 1/2 times 3 to the -2, x plus 5 equals 3. And then to get rid of 1/2, we're going to multiply both sides by 2. 2 will divide out, and we're going to have 3 to the -2, x plus 5 equals 6. And now this is what we have to try to solve. I need somehow to bring that exponent down. I want to solve for x. But at this point, I don't know how to do that. But I want to show you an alternative, something that could have made things easier. It could have made things easier. Let's pretend that I didn't have a 6. Let us pretend, and this is just pretending. It's pretending. I'm going to even write pretend here, okay? Just a hypothetical statement. Let's pretend that what I really had was 3 to the -2, x plus 5 equals 9. Pretend that I had a 9 on the right side. See, 9 is nice because I can write 9 as 3 squared. And then on the left, I have 3 to the -2, x plus 5. And this is the nice thing if I had 9, that now I would have same base on the left and on the right side of the equation. Why is that useful? Well, if I have the same base and I know that the left side must be equal to the right side, same base, and the left side equals to the right side, then the exponents must be equal to each other. There's no way. The exponents have to be equal to each other. So then I would be able now to say that -2 times x plus 5 is equal to 2. I can set the exponents equal to each other. And now I have a simple linear equation to solve. If I divide by -2, I would have x plus 5 equals to -1, which means that x equals -1 minus 5, which gives me -6, just like that. But remember, I was just pretending to show you a very nice possibility. I don't have 9. In fact, I have 6. So right now, I don't have a lot of options. See, if I knew about logarithms, no problem. I can continue algebraically, but chances are that you don't know about logs yet. You will very soon, but right now you may not. So then you cannot continue algebraically. The only way that you're going to have to continue solving for x is to use a graphical approach. And I'm going to show you exactly how to use graphing, how to use graphs to continue with the solving process and to find the value of x. Let me go ahead and show you how to do that. Through a graphing approach, we're going to look at the very last expression that we ended up with. I already invested a lot of algebra into it. I'm going to work off that expression, that equation actually, I should say. If you remember, on the left side of that equation, we had 3 to the -2, x plus 5. And on the right side, we had 6. So essentially what I am doing is I am setting the left part of the equation as a function and the right part of the equation as another function. And this is what I get. So the left part of the equation will be another exponential function. You can see it right here in green. And then the right part of the equation was 6. You see it right here. This is the right part of the equation. And now I am interested in the point of intersection, particularly the x value of the point of the intersection, right here, -5.815. So this is the point that sets these two sides equal to each other. But because all the steps are equivalent, then this x value becomes the x value of the x-intercept of the function. It essentially becomes the x-intercept. So in this way, I can get to approximate the x-intercept as being the point -5.815, 0 for the original function. All right, folks. I hope this lesson was helpful in providing you with two different methods for sketching transform exponential functions. By applying the mapping rule method and identifying strategic x values, you can gather enough points to accurately sketch the graph of an exponential function. Remember that finding intercepts can also be useful, but sometimes it may require the use of logarithms. With practice and a solid understanding of the concepts involved, you can become more confident in sketching transformed exponential functions. Thank you for watching, and I hope to see you in the next lesson. Until next time, everybody. Bye for now.